Go ahead.
All right, so I can go over the top with you right now before.
Absolutely.
Okay. Okay, excited state dynamics and 1D thermoelectric materials. So first, I just go on and explain what the thermoelectric effect is. You have a hot side and a cold side, and then you have some electrons on the cold side. So some of them have more kinetic energy than the other electrons. So since they have more kinetic energy, they're going to travel to the hot side faster than the cold electrons. And then the hot electrons on the hot end together are going to repel the cold electrons. So since you have a dipole on the hot end and the cold end, that's going to create an electric field. And then that's the thermoelectric effect in like 2-3 minutes. Is that good enough for this slide?
Yep. Yeah. Go ahead. Go ahead. There will be a lot of discussion. It's not an exam. You're
Okay.
training and.
Okay, so then this equation z sub t is equal to s squared, I don't know, I think sigma or something, t over k. Z sub t is the thermoelectric figure of merit. S squared is the Seebeck coefficient. Sigma is the thermal conductivity, how well a material conducts electricity. K is thermal conductivity, how well a material conducts heat. And then S is a measure of the magnitude of voltage in a temperature gradient. So basically the higher S is, the greater the thermoelectric effect in the material, and the greater potential it has to conduct electricity, basically. So in the past, researchers have found the value of S by doing experiments on many different materials. So doing all these experiments, people in the past have experimentally calculated the value of S. So basically the whole idea is that researchers want to find materials with the great thermoelectric figure of merit. So then if we do, that means the thermoelectric effect is great. They have a lot of potential to conduct electricity, and then we can use these materials in modern technology like cell phones and things like that. I just wanted to say that we can't calculate the thermal and the thermal and electrical conductivity directly. They can only be evaluated. We can only evaluate this sigma and k divided by T E sub L, and that's called the electron relaxation time, which is essentially the time between electron scattering. So basically, a long electron relaxation time is expected in thermoelectric materials. So that means the greater the thermoelectric figure of merit is, the greater their electron relaxation time is. They're directly proportional to each other. And I just wanted to note really fast that this calculation is an assertion made by materials scientists. And it's by no means definitive. Okay, and then here we have iodide and sodium doping. All right, and then here in figure A, we have the conduction band and the valence band. is the amount of energy dissipated into heat.
Mm-hmm.
All right, same thing here, except we're looking at transitions from IH5 HOMO +5, and then to IE10, which is LUMO +10. And then the same thing here, energy versus time graphs for these same transitions. And then a similar thing here for these graphs. And then the same thing for this transition. Same thing here. All right, and then these are all the relaxation rates of electrons I calculated for different transitions at different temperatures. And here are the decay constants. At this point, if anyone asks, I can just go over this equation, write it out on the board to explain where all these numbers came from. And then the same thing for case of H, relaxation rates of the electron hole. And the graphs I have for that. And that's it.
Okay, very good, very good. Well, thanks much for coming to the meeting. It will be a presentation by Kevin Gima. Unlike most of the Friday presentations, it's not a literature club, but his research update. And Kevin is trying to apply non-adiabatic technique to the understanding and explanation of photoelectric effect in specific materials, and the goal of his talk is maybe multifold. So one is just to check if his research results make sense and are logically consistent, and another one to crystallize the logical stream of goal and expected results for his deadlines about Grolev proposal writing, right? So there were emails with PDF of his talk. There was no time to print, so everyone is very welcome to stop the speaker in the middle and ask questions. So it's more development stage rather than final presentation, and the room is reserved for a couple of hours, so there is no
no need to rush.
Okay, so floor is yours.
All right.
Okay, we'll start from the first slide.
All right. Hi, everyone. My name is Kevin Gima, and I'm going to talk about excited state dynamics in one-dimensional thermoelectric materials. Okay, so before I get into the nitty-gritty of my research, I just want to give some really quick background into the thermoelectric effect. So basically, this is an idealized nanowire. You have a cold side and a hot side here. On this side, you initially have both cold and hot electrons. Those hot electrons have more kinetic energy than the cold electrons. So then the hot electrons are going to go to the other side. And then when they go to the other side, you have a dipole, cold electrons on one side, hot electrons on the other side, and an electric field is created between the two. And then when that happens, electrical conductivity takes place. So that's the thermoelectric effect in a nutshell.
Yeah. So on the bottom of this images A and B, you marked your materials as N-type and P-type, N and P. Is it critically important that one uses doped materials? Can it be Can you tell more about necessity of doping?
You don't necessarily have to use doping for the thermoelectric effect, but a lot of scientists dope materials to strengthen that effect. Okay, so this equation right here, ZT, that's known as the thermoelectric figure of merit. This S, that's the Seebeck coefficient. I'm not sure what the symbol is. Sigma. All right, sigma is the electrical conductivity. K or chi, that's the thermal conductivity. And then the Seebeck coefficient, that measures the magnitude of voltage in a temperature gradient. All right?
Is it okay to?
Yeah, go ahead.
Can you go to previous slide and look on it for a little more? So, what is difference in the electronic structure of materials when they are cold and hot? What's the main principle? Why voltage will be different at hot and cold side? What changes? Which property of material is changed when they are heated or cooled?
Their kinetic energy. When you heat things up, they get more kinetic energy.
Is your Fermi energy affected?
Yes.
No.
I
The question is good, but Fermi energy shouldn't be affected.
okay.
Fermi distribution should be affected, and it is an answer that I want to hear.
Okay.
So what is changed after material is cool or hot?
Fermi distribution.
Okay, tell us what is Fermi distribution. Just generally from what you.
Fermi distribution is the distribution of energy among the different electrons.
Occupation. You wanted to say occupation of different orbitals, right? So at zero temperature, all orbitals below Fermi energy are occupied, and all orbitals above Fermi energy are unoccupied.
All right.
Does it stay the same at elevated temperature?
No.
How does it change? Can you draw Fermi distribution? If no, just make mark for yourself and keep going.
Are
Okay.
these semiconductors, conductors, insulators? I guess I don't know what your N and P type materials are. I would assume they're semiconductors since you have lead telluride. I think it's telluride.
Yeah, this is lead telluride with sodium doping and iodine doping.
What do you know their band gap? Is the band gap small enough that thermal?
Otherwise, it will not work. So
Okay,
it should be
so it should be very, very
low
small.
gap semiconductor.
Okay.
All right. So yeah, I explained what the thermoelectric figure of merit is, what all these symbols are. So the Seebeck coefficient measures the magnitude of voltage in a temperature gradient. So the higher the Seebeck coefficient is in a material, the greater the thermoelectric effect is in that particular material. So in the past, scientists have found out the magnitude of the Seebeck coefficient for different materials experimentally.
So once again, what is this S capital? How does voltage appears due to gradient in temperature? Can you analytically think what's the principle? What does change? So if you heat material, it changes Fermi distribution.
Mhm.
So some orbitals get occupied, and the occupied orbitals have different spatial distribution, and it forms voltage. Is it how it works? Like why voltage appears due to temperature gradient?
voltage appears due to temperature gradient because so some of the electrons have more kinetic energy than some of the other electrons. So therefore, those faster electrons will get to the other side faster. And then so then you have hot electrons on one side, and then the colder electrons on the other side. You have a dipole, and an electric field is formed between the two ends.
So you interpret it more from a classical point of view, without figure, without orbitals. Okay. Yeah.
When you say hot, do you mean thermally hot or electronically hot?
I mean thermally hot.
No, electronic.
Electronic.
Yes.
Okay. So then your P and N type are important because one will have orbitals, like one is lacking in electrons and one has extra electrons, so that will facilitate a current. And since you have hot and cold temperature ranges, that would do different Fermi occupation, and that causes a flow,
Mm-hmm.
right? Okay. So can you do it without PNN materials, or do they have to be PN materials? Because I thought before you said they don't have to be doped. But if doping causes the occupation of orbitals in a way that facilitates this, wouldn't you then just want to dope it? So that you don't have to find the specific material that has these properties? So in other words, isn't it easier to just dope a material than to scan through hundreds of different materials to try and find the correct one?
Yeah. I mean, like I said earlier, there is like still the thermoelectric effect still happens in some materials. However, the doping process greatly strengthens the thermoelectric effect. If that.
Okay.
Right. I share your concern, and I would answer so that one needs an interface between two materials, which can be either two semiconductors of different nature, or semiconductor of the same nature but with opposite doping.
Okay.
All right, so researchers want to find materials with the great thermoelectric figure of merit. The higher the figure of merit is, the higher the thermoelectric effect is in that material. So basically, calculating electrical and thermal conductivity is also something of great interest for scientists. It's generally believed that scientists can't calculate electrical and thermal conductivity directly. They can only evaluate electrical and thermal conductivity divided by the electronic relaxation time, all right, which is the time between electron scattering, all right. So a long electronic relaxation time is generally expected in thermoelectric materials, all right. And I just wanted to note that this earlier statement that I just said a couple seconds ago, it's a claim made by material scientists. It's by no means definitive. So I just wanted to point that out. Okay, so since the PBT nanowires I studied were doped with iodine and sodium, I'm just going to briefly talk about iodine and sodium doping in case you guys forgot. So here in figure A, we have the undoped material. In the side A, the covalence band and the valence band remain unchanged. However, in sodium doping, when a valence band becomes empty, so this band right here becomes empty. However, in iodine doping, one of the covalence bands becomes filled. All right. So just a quick refresher on iodine and sodium doping. And here are the elements in the periodic table. We have sodium, thallium, lead, beryllium, and iodine.
Kevin, so what is specific about iodine and sodium, or maybe instead of sodium one can use thallium? What are their valence, number of electrons on the outer shell? Which oxidation states do they take? How? What's the logic for selecting iodine and sodium as doping agents?
Okay, so sodium, since it's on the far left end of the periodic table, sodium has only one valence electron. That means it only has one electron in its outer shell.
And lead?
Lead has about
If you're not sure, just request help from the audience.
Alright, guys, I'm not sure if I'm 100% correct on this or not, but I believe lead has 4 empty spots in its outer shell, if I'm correct.
Yeah. And the D and F orbitals are relatively low in energy.
Mm-hmm.
So then it would have 4 valence electrons.
Okay. Alright, any other questions about this slide?
Can you go back a slide? So if you don't dope it, you have A, right?
Yeah.
So then your Fermi distribution, you have to have enough kinetic heat to promote an electron past the band gap. So you virtually have to have a conductor if you don't dope it.
All right.
correct?
Mm-hmm.
Where if you dope it, then your band, like your band gap, there is no virtually band gap because you have unoccupied states immediately above your occupied, right? So if you say no doping, then you have to have a conductor.
Mm-hmm.
And everyone agrees about oxidation. The most typical oxidation state for lead is 4.
I thought it was 2. I would say 2.
Okay, so lead is ready to donate 2 electrons for chemical bond. And sodium 1. Okay. And what about tellurium? How many electrons does it want to accept?
2.
Okay. So it's stoichiometric. Lead telluride 1-to-1. Lead gives 1, tellurium takes. Or lead gives 2, tellurium takes 2.
Okay.
So why and iodine? How many electrons does it take?
It only needs one more electron for its outer shell to be filled.
Okay. So therefore, if it replaces telluride, it fills the conduction band with an extra electron.
Yeah.
Okay.
So, is thallium circled because it's an alternative to sodium, or is
Yes.
it circled because you're using it?
It is alternative to sodium, and from logic, it would be much more natural to use neighboring periodic table. But by some unknown, at least to me, reasons, in experiment people use sodium, which looks a little crazy,
And it's much smaller, so you would have lattice strength.
which is strange. I would use thallium if I would like, fabricate it from scratch.
Alright, any more questions on this slide? Or any of my other slides? Okay, now that we got the background out of the way, we can start talking about my research project. So basically my research project is to calculate electronic relaxation rates for lead telluride nanowires, and I want to calculate electron relaxation rates in Interface 100, which is this model right here, my PVT nanowires. You have the sodium doping and the iodine doping. So I want to calculate electronic relaxation rates for this model in different temperatures.
So is your interface 100 the mu, is that the indices, or is that not talking about crystallography? Because like you can have 110 or like 111. So is that crystallography where you cut along a plane?
Oh, yes.
Okay.
And mark for yourself to make a slide on Mueller indices
Okay.
next time.
Is it common to say 100?
I would say 100.
Oh.
I want to determine their dependence on temperature fluctuation. So since this hasn't been that well studied in previous literature, my advisor and I thought that this would be a good thing to look into. All right. So the methodology, how I calculated these relaxation rates. All right. I calculate the couplings for the interfaces first. To do that, I perform heating computations for both interfaces. Right now, I just did only interface 100, but in the future, I plan to work with an interface 111 also. And then I do molecular dynamics for both interfaces. And then finally, I can perform the coupling calculations. I use the MATLAB code to calculate red field tensors, which is this thing right here. Let's see. So the x and y axes right here are the orbital indexes. All right. And this log, you might not be able to see this clearly, are ij. That's basically the rate of transition from orbital I to orbital J. All right. So that's red field tensors, and then finally I use the MATLAB code to calculate electron dynamics and charge transfer rates.
So can you explain heating, how you did heating? Because as of now, it seems like you need a temperature gradient. Did you do a temperature gradient, or did you just do a system that you heated to a certain value, you looked at the properties, and you heated a different system to a different value and compared it? Does that make sense, the question?
Okay, so first in my model, I did regular heating. I heated it to a certain temperature, and then I got my outcome file and all my other files for that. And then I took those files and then did molecular dynamics on those files.
So you didn't have a temperature gradient?
You just heated it at certain temperature,
it's-
not.
Okay.
Levi is not trying to undermine the quality of work, he just tries to find the logic.
Okay.
And set of approximations.
So, yeah, I'm just wondering why you use the 3 atomic layer in this pattern now. Because you said you have a plan to work on one interface.
Right.
In that case, you cannot make a 3-layer stochastic. I'm just wondering.
No, the question is fine, the question is fine. I'm curious to hear the answer.
Can you repeat your question again?
So why you choose the 3 layers instead of like 2 or 4? I mean, even number.
Is this
what-
your actual
Is
atomic
actual
system?
image
This is the
or
full
image?
model.
Is it actual or model?
This,
You mean is this
No, I
picture
mean,
my
in
phone
the,
on?
in the left side. you
Oh,
can-
this one.
Is actually your system or is just a schematic figure here?
It's just a schematic figure.
Okay, then never mind.
No, it's a true model.
That's a- So it's a 3x3 by
Like 32, if that's the true model, because I've counted it.
How many?
It's 32 in the Z. Yeah,
So it's 32 by 9,
Thickness is 300 millimeters
Yes.
or
but it's square. So it's 9 items.
no, okay.
So 9 by 32.
is there a reason that your iodine dopants and your sodium dopants are seven layers apart from each other, but they're 8 layers apart from the other one? I mean, that one I'm just curious on.
I can answer, but I'm curious to hear what Kevin is thinking.
I am not exactly sure about that.
Just homogeneously distributed, as homogeneous as possible.
All right.
Iodine and sodium replaces different sites. Therefore, you cannot make the offset even number.
Okay.
Make sense?
Good.
And total number of atoms is even, right?
Looks
So
like it.
it's possible across stoichiometry.
And you want it, so is it on the surface of one of the sides or is it in the core? So like if you cut the layer that you have the dopant, is it here or here? Like this is the layer and you cut it, is the dopant here or is it in the center?
So you're saying if I have a nanowire and I cut it in half?
So like if you, like the fourth one from the bottom, you have telluride, then the blue, then telluride again.
Mm-hmm.
Is the dopant replacing the lead that's on the surface, or is it replacing the telluride that's in the interior that we can't see?
It's replacing the lead.
Okay. So then why would you want to put it on the surface and not put it on the interior?
That's interesting. If Kevin, if you play this visualization software in the book, you probably will be able to answer that it is on the interior.
Okay.
And if you show it as it is placed on the interior, then outer layer will block it from human vision.
Yes.
So it is intentionally exposed for illustrative purposes.
I guess I assumed that. I just was.
No, thanks much. It's what we need to do to discuss all little issues and moments.
Okay, so these are the four occupied orbitals I've studied. So IH12, 5, 3, and 1, my HOMO orbital. On the left hand side here, as always, this is my model, and these violet circles are my orbitals. And yeah, and
Wait, can I stay a little longer? So those are occupied orbitals.
Yeah, occupied.
HOMO and HOMO minus something.
right.
So molecular orbitals, quantum orbitals are composed of atomic orbitals. So which atomic orbitals contributes at most to composition of these orbitals? Are they mostly localized on lead or on telluride? Are they more S character, P character, or D character? Just how do you interpret what you see here? Like your model does have bright green, dark green. It's likely that your bright green is telluride and dark green is lead, right?
Right.
Okay, so on which atoms the atomic orbitals are appearing, on dark or bright?
The dark ones.
Can you show me example where it appears on dark ones?
I'm just going by visualization here.
Yes.
Like here is, like right here, the orbitals where they appear here. This is dark. Here, right here, this appears to be dark.
What appears
No,
more
it's-
frequently?
It's light.
On
That's
light
light.
or dark?
Like if you go here, at least on Homo, this is pretty obvious that these are the light ones,
All right.
right? So that would be Telluride,
Okay.
where like here's the dark one, nothing. Here is a little bit, but like these have nothing, right?
Mm-hmm.
So through community effort, it looks like it's localized more on tellurides.
Okay.
And what's the shape of these atomic orbitals? S, P, or D?
All right. Wait. S is the circular. P is the dumbbell. P.
Okay, so your occupied orbitals are composed on atomic P orbitals localized on telluride.
Mm-hmm.
Good. When you will be presenting to a bigger audience or write a paper, reviewers will definitely ask it, so it's better to figure out ahead of time.
Okay.
Could you guess what your unoccupied orbitals would be located on? If not, it's not a big thing.
Because it is on the next slide, right?
I don't know, what's on your next slide?
Oh,
yeah.
It looks like corn with butter.
Yeah, it looks like corn.
Summertime.
So why we are looking on this specific on this orbital? Because we have no wires, right?
Yeah, there's no,
So what is the significance of a specific number of orbitals?
The significance of the specific number of orbitals.
why do you
Why
want
we are looking on these orbitals?
So we're looking at these four orbitals because in the MATLAB calculations I did, for example, in the calculations I did, I calculated the relaxation rates for the electron and the hole. For instance, for an electron when it goes from this orbital, which is IH12, to this orbital, i.e. 15.
So you
the-
selected the specific orbitals as your initial conditions.
Yeah, based.
And you want to illustrate what were your conditions.
Mhm.
Did you ever produce a DOS or PDOS?
A PDOS file?
Projected density of state?
No.
Do you plan to?
Yeah,
Just because right now, looking at like LUMO plus 7, LUMO plus 9, LUMO plus 14, or LUMO plus 19, it's hard to understand the energy that you are exciting. Because as of right now, it could be within 1/10 of an electron volt, or it could be 5 electron volts. So it's hard for at least me to understand what is happening with the electronics, since you don't have much energy to excite from whatever to whatever state you're going to.
Or
Right.
in other words, why you choose these initial conditions like I-15?
So I was pressed for time, so I chose these initial conditions at random. So if I had more time, I would have made my OS strength file, and I would have used the orbitals from those to determine my initial conditions according to decreasing oscillator strength.
But oscillator strength is not involved because you're not using a photon to excite. You're just using heat. So the energy difference is the most important, not selecting the transitions that have energy resonance and are bright. Is that right?
So it would be more reasonable to just systematically scan all orbitals in the vicinity of the gap. As
Yeah,
initial conditions.
so it might not be that applicable for the photo, well, I forget the name of the application, to go to home, E15, because that might be too far outside of the Fermi distribution that will ever be seen in reality. Does that
Correct.
make sense?
Yes, so thermal excitation may not reach to orbital so high in the
Yeah,
conduction.
because I think it like falls off exponentially.
Depends on temperature. What's the temperature?
So I haven't gotten to temperatures yet, and
And you can tell just by words,
What is the
without
temperature?
showing. Just range of temperatures that you explore later.
so the ranges of temperatures I explored are 300 kelvins, 500, 700, 900, and 1100.
Oh, that's a lot.
So let's go to the same question as on the previous
Yeah.
slide. This orange bubbles.
No, go to the next slide.
So, which atomic orbitals contribute at most to form the unoccupied orbitals? Are those,
It seems like those are the dark ones.
okay, so
Right.
lead.
Yeah, lead.
And from these images, do you see are they s orbitals or p orbitals?
Okay. So they look like s orbitals.
Well, because if you rotate p orbital and look on a certain angle, it will block its internal structure.
Okay.
But if you open the first one, i.e. 8,
Mm-hmm.
it looks like there is a minimum.
It's like a node.
Yeah. Yeah, of the atom. So it's you may double check later, but it could be either it could be not only s but p orbitals on
Okay.
that as well. Another question on this image. So for IE10, which is like 1 + 9, the unoccupied orbital is delocalized almost over the whole model, or at least in the space between two dopants. And it looks homogeneous. But
You mean
on-
between here and
Yes,
here?
yes,
Okay.
yes. But in the orbital IE8, which is 1 + 7, it is localized only in the very narrow range. So how do you interpret it? Why orbital decides to sit in this localized spot?
And that's where the dopant is, right?
Mm-hmm. Just repeat what Levi told. So on the orbital IE8, there is a substantial part of this orbital contributed from the dopant, from the iodine,
Okay.
and a couple of nearby leads. So the doping atoms, doping elements contribute specific orbitals.
All
They
right.
are localized not over the whole material, but only in the vicinity of dopants.
Okay.
And it is intentional goal of doping to create localized states around doping and contribute another and to have the states in the certain states of certain energy and certain occupation in the density states. Okay, please keep going.
All right. I'm gonna skip this slide. It's not too important. Alright, so meaning and structure of the PPE and PPH variables,
What is PP? Oh, wait, no, man.
population.
No, it's a very legitimate question. Please ask and.
Oh, you skipped.
Population of electron orbitals, and population of the electron whole, of the whole.
Okay.
So you may add that it is the main outcome of the code
Okay.
that you got here. At each run of the code, well, you should tell it, not myself. Keep going.
So you're saying I should, at each iteration of the code, at each loop of the code, I calculate the population of the electron orbital and the population of the whole. Alright?
Mm-hmm.
So right, PPE population of the electron orbital has two indices. One is the time step, and another index is the number of orbitals counting from LUMO and up. So you have LUMO plus 1, LUMO plus 2, and so on and so forth. PPH is almost a similar same time step, but however the second index is slightly different. So it's counting from HOMO and down. So HOMO minus 1, HOMO minus 2, so on and so forth.
And wait, what is stored? Is it just the populations?
Yeah, the populations of the electron orbital and the whole is stored. And these are a few MATLAB commands we can use. Waterfall PPE gives you the population of the electron orbital. Waterfall PPH gives you the population of the whole orbitals. And this code right here merges the populations. Alright, and then this is a graph of the population of orbitals. Z-axis is the population of the whole orbital. The bottom axis right here is the time steps, and this is the orbital number.
So how do you interpret this figure? Which orbital, for this specific example, which orbital is excited at time 0?
Okay, 1, 2, 3, 4, 6.
Okay, what is the, so at time 0, only orbital number 6 has occupation equals 1.
Right.
What is the occupation of all other orbitals?
At time 0, it's just 0.
Okay,
Is that HOMO plus 5 or LUMO, or HOMO minus 5 or LUMO plus 5? Because you have IH or IE in the bottom there.
Maybe this is just an example.
just an example, but here it's likely HOMO minus 5. Okay, and what happens to occupation of this orbital number 6, HOMO minus 5 as time goes by?
As time goes by, the occupation decreases to 0
Okay, and where does occupation go?
into these other orbitals.
Does it go immediately to all of them?
No, not immediately.
So what's the mechanism? How does it go to other orbitals?
Step by step?
Yeah, just design some verbal formula to explain what you see here.
So what is the line shape indicating?
Direction.
I mean, why is going up and down?
Like if you look on the orbital number 5,
All right.
Can you describe what is going on with it?
Okay, so for orbital number 5, for the first couple of time steps up to 400, its occupation increases, and then after that time step, it decreases.
Why it decreases? So it increases because it soaks population from orbital 6.
Mm-hmm.
And why it decreases afterwards?
Because its population is going into these lower orbitals.
Okay, so lower orbitals get population not immediately from the initial orbital, but in a sequence,
Alright.
subsequently, right?
Right.
Good.
So, do you think orbital 3 and 4 that stay relatively low have population going into them? Or could it be that once they get populated, within a matter of a few time steps, it immediately goes to orbital 2? Or in other words, did you ever look at your non-adiabatic coupling terms to see if the non-adiabatic terms are large going from 5 to 2, or if it's large from 4 and 3 to 2? Does that make sense?
To formulate question a little differently. Do you intend to perform analysis and then repeat your question?
Yes. So your Redfield tensor, the one that you have like the image with all the bars,
Yeah.
right? That tells you how fast orbitals will lose population to another one,
Right.
right? So will you later on look to see if there are specific orbitals that will quickly dump their population to a different orbital to understand possibly some physics of your system, to try and come up with like a fundamental understanding? Or are you just thinking of doing a lot of these and saying, oh, we see the trend?
I plan to do that in either the near or far future.
Okay.
I first want to study interface 111.
And answering the question of Levi, not in the whole depth, but just verbal addressing. That there is a simultaneous exposure of subsequent relaxation through the chain of intermediates, and parallel, where several channels work at the same time.
Okay, so interpreting the graphs.
Interpreting what?
Interpreting the graphs. I'm talking about these blue graphs.
Oh,
So-
graphs.
Yeah.
I heard grass.
Sorry, I meant graphs.
We have snow out today, so we had to look at the snow.
So we're not interpreting the grass anymore.
Okay, so the background color, which is just this blue color, that means there's no difference from the ground state. Brighter yellow, negative charge localization. So here that means there are more electrons in this region compared to the other region. Darker blue.
Can I ask something before you complete this?
Sure. About this slide or the previous slide?
About the connection of the slide, one slide before that and one slide after that. Do not go there yet. Just let's chat, and then you will show it if needed. So one slide before, you are showing set of occupation trajectories.
Okay.
Like amount of this trajectory is discrete, like 6 or maybe 10 or maybe 100, but not much.
Right.
Discrete set of lines. And on the next slides, which right now you are giving guideline how to interpret next slides, you are showing graphs, three-dimensional distributions, which are continuous.
All right.
So what is the connection between this discrete set of occupations and this continuous distributions? It looks like they're very much connected, but what is your impression how they're connected, or where should you look to bring up this connection?
So you mean how my graphs on the next slide connected with my population of electron holes
Exactly,
in the
yes.
previous slide?
Yes, yes.
Okay, so I know that from the previous slide, it tells you how the population of that hole varies with time and with electron change.
Mhm.
So since the dash line here since the dash line like right here is my electron hole.
Expectation values.
Right.
Okay. But the overall graph, this three-dimensional distribution, how does it originate from certain trajectories of occupations?
Wait, are these just like two like slices of that graph, of that three-dimensional graph?
How, so your y-axis says z angstroms.
Mhm.
What does that mean?
Z angstroms, that means atomic distance.
Okay, so you went from a three-dimensional to one. How did you do that? So if you're showing z and you, what happened to x and y? You integrated, right?
When you were doing Bandel 5, you integrated along x and y.
Right, so now you look at how much electrons are as a function of z.
Okay.
And that is per orbital, right?
Okay.
So then when you did this, you had like your population times that orbital, right? So then you had some graph and you kept adding that, right? So this gives you spatial distribution, where the other one gives you just bands, right?
Mm-hmm.
So they're connected, but this allows you to know where it started and where it's going, right?
Mm-hmm.
You agree with Elaine?
Yes.
You will be able to explain it to everyone?
Okay. So if I understood what he said correctly, in the previous graphs I was looking at three dimensions.
No, you're just looking at the band population.
Occupations of orbitals. Right?
Yeah, yes.
All right, and then I integrated along the x and y axes of that previous graph.
Of orbitals that you were showing at the very beginning. Right?
All right, so I integrated along the x and y axes of the orbitals.
Yes, you did.
All right, and then that gives me these graphs right here.
Not yet.
No. Right. So let's say these are your things.
Okay.
And now, right?
Mm-hmm.
So this is what you have
Okay.
before this, right? So when you go here, you start by saying, oh, it's all this one, right? So you have a lot, and a lot, and a lot. And as you go, it gets more and more diverse, right? Because now you take, this is, wow, this is terrible. Sum n equals 1, 2, 2.
Okay.
Right? Right, so then you say P n psi n. Yes?
Mm-hmm.
So this P is here, this psi is here. So this only gives you which orbitals are populated, where this gives you where it is in the nanowire.
All right.
So then that could tell you if it's going from one side to another. Yes?
Yes, very good, very good. So you, in order to generate these blue figures, you add together all orbitals that you have.
Okay.
But each of the contributing orbital comes with different weight, which weight ranges from 0 to 1.
Okay.
At each point of time, there is one orbital contributes more, other orbitals contribute less. And when you add them together, you get this dynamical figures.
Okay.
More or less reasonable. So next time you present, you should explain things like Levi did.
All right.
Okay?
And remembering that you take that function minus the ground state. Yes?
Yes. Yes. Perfect. And the green figures, what's the connection of green figures and occupations? If you,
Oh, this one?
yes. So they also look continuous, right? Continuous distributions of time and energy. And the question is, how do you generate these figures based on the discrete set of population trajectories? How you convert occupation of each of the orbitals into this distribution?
You use something similar to that. Okay.
Okay, so something similar to that. I'm going to make a guess. This P sub n sub t remains the same, but this is replaced by the energy at each orbital.
Delta function centered at energy of each orbital. Yes. Perfect. Excellent.
All right.
Now please return to your guideline to interpret.
Okay, never mind, I'll wait until.
Yeah, now keep explaining this guideline to interpreting the distribution figures.
All right, darker blue is positive charge localization. Solid line is the electron expectation of energy, and the dashed line is the electron hole.
And maybe we made a mistake. It's misguided you. It's opposite. Like solid hole dashed electron.
All right, so never mind. The solid line is the hole. The dashed line is the electron. Okay, so you see here at for 300 Kelvin, 500, 700, 900, and 1100 Kelvin. For each of these, the model is right here. So then, at the initial time, the electrons are right here at around 15 angstroms, and then at later times, some of the electrons travels here to around 30 Kelvin.
No, it's 30 angstrom.
Oh, angstroms.
So I might have misunderstood. So the dark blue means that you're gaining positive density?
Right.
So you're gaining positive density the entire time, so that means your structure deviates from the ground state everywhere. Everywhere? Where do you have similar density for the ground and excited state? Because on your other one, you have a range and there's 0. What color equals 0 here? Because you took the difference. So you have positive and negative. Where's 0?
I'll probably take responsibility for this question because it's too much on Kevin. The procedure to determine 0 was performed for energy distribution and was not completed for this part.
Oh.
And the nature, if the dopings, P and N dopings have similar nature and similar localization character, the 0 which will be colored in green will be found naturally. But since they are of different physical nature, orbitals corresponding to holes are more localized, and orbitals corresponding to electrons are very localized, different level of delocalization. And therefore, if one looks on these 3-dimensional pictures, the midpoint between minimum and maximum will be not on the 0 level, but will be shifted to the positive.
Okay.
So it's a little misguiding.
Okay, so it's just a shift.
Yes,
Okay.
yes. So the color code, like light blue would correspond to 0 in this, but it is yet procedure in development.
Okay. That makes a lot more sense. I was like, you're gaining positive charge the entire time?
No, no.
Wow.
No.
Let's make this material. We'll make millions of dollars.
No, no.
Alright. So yeah, the same thing here. Some of the electrons go from here to here. Similar things happens for 500, 700, 900, and 1100 Kelvin. For each of these, the model is lined up right alongside these graphs. Any questions?
Yes.
Other questions about the
Yes.
slide? Yeah.
Yes. What's the similarity and difference in your maps of dynamics for different temperature? What is similar in all of these five graphs, and what is different?
Okay, so what's similar is that the electron hole, which is this solid line right here, remains constant for all 5 graphs. It's just sitting at 20 angstroms here. So that's what's similar for these graphs.
Okay. What else is similar? What
I
is-
guess the electron displacement. So for all 5 of these graphs, the initial where the electrons were was at around 15 angstroms, and then at later times, all the electrons arrive here at 40 angstroms.
Okay. And what is different?
I guess what is different is that in some of these earlier graphs, for example, the 300 Kelvin, most of the electrons didn't really go anywhere.
So the rate.
So in all 5 graphs, the in average electron tends to go from, as you say, 15 to 40.
Right.
But at which time does it go there? When it goes earlier and when it goes later?
All right. So some of the electrons start moving at -2 picoseconds, and then at a later time, which is like around half a second, most of the electrons are here at 40 angstroms.
So how does the time when electron decides to go depends on temperature? Like look on 300 and 1100. So here is when where it moves on sooner and when it moves on later.
So on 300 it moves sooner, and then on 1100 it moves sooner, and then on 300 it moves later.
And how can you verbalize it in a general form? How temperature affects the rate of electron migration?
Temperature is inversely proportional to the rate of migration.
So if you do 1/T, that will, the bigger the T, R will get smaller, right? If it's inversely proportional.
So if you measure the offset on the time scale, it will be time, not the rate. So the time when electron goes on maybe is inversely proportional to temperature. And rate is inverse of this time, right?
So it's directly proportional.
Yes. So the higher the temperature, the quicker electron goes.
All right.
It's your discovery that you want to claim when making a paper.
All right.
The higher the temperature, the quicker electron goes.
But this goes from one iodine to another. Right.
Sure, maybe. In this example, yes. But there will be different conditions, and this statement will likely be generalized, not only from one iodine to another. Okay.
All right, and then here we have the energy versus time graphs from our HOMO orbital to LUMO plus 7. These are the 5 graphs, and then our distance from the hole to the electron. So this distance right here. That is the amount of energy that is dissipated into heat. All right, so for the 300 Kelvin, it remains relatively constant. Delta E remains relatively constant. But then as the temperature increases, the delta E also changes.
So it looks like your system is, there's no bang gap. Is that right? Or at least for like 900 and 1100, like at 900 it looks like the yellow and the dashed, you can't really tell the difference between the black.
It would be really great if there is no band gap. It would be good for thermoelectrics. But let's formulate the question the following way. Do you intend to double check that this material has zero gap?
Yes.
And it may not be correct. It needs to be double checked.
All right.
Next time you do this talk in the improved version, you may start results from standard things like density of states that will explicitly show the gap.
Okay.
And it also might be good for this, you go from like -3 to 3 it looks like, where there's nothing happening below 0 and nothing happening above like 0.5. Right, so you could expand it so it's, the resolution's greater, if that makes sense.
You mean lower the range on my y-axis?
Yeah.
So I can see more of the graph?
Yeah.
Okay. All right. So here are some 5 more position versus times graphs from HOMO plus 4 to LUMO plus 9. Again, here we have the same thing happening. The rates are becoming shorter as you increase the temperature.
So let's chat more about this one. I have doubts, not doubts, intentions for double check about the expectation position of the hole for the black line. But for electrons, it looks very reasonable here, and it partially addresses the previous question of Levi. So, what if the original orbital from where electron starts, the orange things?
H5?
Not the hole, but
Oh,
where is
sorry.
the original orbital for electron, and how does it look in space? Remember, your previous question was, is it right that it goes from iodine to iodine? What is, probably it finishes at the same iodine in all these figures, but where does it start from?
It looks like the center.
So it is
Between the filters.
distributed, delocalized, right? So it's above the dopant level, delocalized state.
But the question still remains, is that is HOMO plus 5, HOMO plus 4 thermally accessible in the application, or do you need light to do it?
Or would it melt if we heat it to populate this state? Yep.
Alright, and here are energy versus time graphs for HOMO plus 4, LUMO plus 9. Again, you can see a similar things happening for the previous, as compared to the previous energy versus time graphs. Any questions about this slide?
So it's the same trend.
Mm-hmm.
Higher, the higher the temperature, the quicker the relaxation.
Right. Alright, and here are position versus time graphs for HOMO plus 2 and LUMO plus 19. This dashed line is the electron. As you can see, it does a sharp decrease in
Expectation value?
yeah, in expectation values, and then it goes back up. And I am unsure if this is normal or not.
So how would you interpret it? And I think Levi can assist you with that.
Okay, so at a very low temperature, as time increases, the expectation value for the distance does a sharp decrease, and then at later times it increases. But then as the temperature increases, you see this dip becoming less and less pronounced.
So why it goes down? Highly likely that dopants contribute more than one states, and there are localized states higher up in the conduction band. And just by coincidence, your IE20 is one of another dopant localized state. So you
Okay.
start from iodine, then as it relaxes, it goes to delocalized state, which is distributed over the whole system with a center near zero. And then as we go deeper and deeper, it finalizes on the lowest state, which is localized on iodine. Therefore,
Okay.
it makes this strange trajectory of charge. But this looks trustable.
So, looking at all of this data, do you, and so before, your z-axis is periodic, right? So the bottom is right above the top.
Right.
In your periodic cell. So do you think, since you have 6 layers between the bottom sodium and the top iodine, that could play a role in messing or like stabilizing the iodide at the top versus the bottom, because there's 8 atoms between the middle iodine and the middle sodium. Does that make any sense, what I'm asking?
So you're asking it is if the two if the sodium doping here and the iodine doping here is what's playing a role in these dips?
Yes, somewhat. So in the first one, we saw that it started at the iodine close to the soda. Can I use your laser? So it started on this iodine
Okay.
initially, and then it moved to this one.
All right.
So my question is, since you have a larger gap here compared to these 3 and these 3, could that be influencing your result on going from one iodine to another? Where, since the chemical environment is slightly different, and since it's all periodic, that might be the reason why the 2 iodines are not acting similarly. Or the other thing, if you shifted your cell, then your PN, right now it looks like your PN junction, the center is where you have no dopant. Where if you shifted it to have the top iodine where the top sodium is, right?
Then if you show 2 PN junctions in one cell.
No, shifted it down so that the iodide becomes sodium and sodium becomes iodide.
So the qualitative distribution of this three-dimensional shapes will remain the same,
But
but
it
the
would
definition,
appear that it will,
definition of expectation value will be affected.
yes, and then it could appear that you're having transfer towards the sodium instead of transfer away from the sodium.
Generally, the concept of expectation value is not well defined for periodic conditions. One needs to talk only about momentum.
Yes,
So
because
it's-
like right now, it looks like your electrons are going in one way, which I don't know if that's the right way it should go, or if you just change your frame of reference, then it would be more physics-y. Yeah.
Have you tried doing calculations without the outer tube, or just the inner tube, and then have more doped?
No, I haven't tried yet. All my calculations are with this model.
I think that might answer the question, then, if
Yeah.
it doesn't go out that
Just
direction.
bring in a little bit of vacuum.
Or that.
Wait, so you're saying that I should try calculations where I remove like one of the doping materials and see how my expectation values change with that?
He suggests to break the conjugation. Right?
More.
All right, I'll keep that in mind. All right. Here you have your energy versus time graphs for the same transitions.
I have a question.
Yeah.
It's a serious concern about to double check. The label on the top tells that for all 5 graphs, it is from comma -2 to luma +19. And it is supposed, there is an expectation that energy of this transition is the same independent on the temperature. But these graphs show offset from at 0 time is drastically different. So it's, are you planning to check that it is indeed the same initial condition for all 5 graphs?
Yes, I will check it.
Because it is very strange that in one place the initial excitation energy is less than 1 electron volt, and in another one it is more than 2.
All right.
It shouldn't be this way. Yeah, please check for.
Is this the case where you have the lowest and highest, like, is this the case that this is your highest excitation energy? So like if you take the energy of H3 minus energy of E20,
Yeah.
is that the highest energy, or is there another case that you have even higher excitation?
I haven't checked that.
Oh. Oh, no, this is definitely higher.
All right, and these are my position versus time graphs for HOMO +11 to LUMO +14. Do you have any questions? All right, say the same thing here. Professor, are you concerned about this graph like you were 2 slides ago?
Oh, yes, please double check.
All right. Okay, but finally, these are my calculated electron relaxation rates. These are the graphs I have in a table. This is a better graph. I made 5 graphs, one for each temperature. On the x-axis, we have the energy difference. energy of the unoccupied orbital we're looking at minus the energy of the LUMO orbital of the x-axis, and then the natural log of the electron relaxation rates. So when I graphed them, I got all five lines. The R squared values are really strong, except for this one. I'm not exactly sure why there's a weak correlation. Maybe it's because of this single data point. That's something I have to look at. But I have decay constants for all five temperatures, which is the slopes.
So what,
Let's talk more about this.
okay, what is a decay constant?
Alright. I'm going to write on this board right here. Alright, so the relaxation rate of the electron is equal to some constant times an exponential of e to the negative alpha delta e. So delta e is the same thing as this x-axis right here. If we take the natural log of both sides, delta E. This is the equation I was keeping in mind when I was graphing this. So this is my y-axis, and then this is my delta E. So the decay constant I'm talking about is this alpha thing right here. So
This formula would imply that your intercept is 0?
my what is 0?
Your y-intercept. Because, like, you think y equals mx plus b,
Mm-hmm.
you have mx, and then you don't have plus b.
Well, you have the logarithm if you break that up.
You see,
Oh,
so
okay, yeah,
in the
yeah.
denominator.
All right, so this alpha, that is what I mean by my decay constant. Does that make sense? I'm basically, essentially trying to fit an exponential, or in this case, a linear fit to these values. Does that make sense?
So you're trying to fit your observations into the gap law, right?
Mm-hmm.
So then why are some of your alphas positive and some negative?
Like which of these lines look intuitively correct and which look strange?
The graphs at the later times, the 700, 900, 1100, they look okay. The 300 and the 500 look strange.
So how do you interpret the top three lines? Just verbally, what does it mean for your equation that you plotted? The red equation on the whiteboard.
So because of their R squared values are a really strong point, like 885, that means this equation is a very strong fit for the data.
But explain again this equation, physical interpretation of the very first equation.
Okay, the electron relaxation rate, Ke is equal to some constant times an exponential, which is e to the negative alpha, which I called my decay constant, times the change in energy between my orbitals.
So when, according to this equation, when relaxation is quicker, for larger gap or smaller gap?
So for this equation, relaxation weight is bigger for a larger gap. No, smaller gap, smaller gap. Alright, because of the negative side, got it.
Okay, so you expect that smaller gap gives quicker relaxation.
Right.
What is the background? Why it is so? Why smaller gap gives quicker relaxation?
Smaller band gap gives off a quicker relaxation. Because I'm using my classical intuition here, an electron travels shorter distances between two closer orbitals.
But it's between orbitals, it's energies, it's not distances. So smaller energy offset gives quicker relaxation, but I agree with your intuition that going through smaller offset is easier, but these are additional intuitive background. Where does energy go when electron relaxes from one orbital to another?
So when it goes from a higher orbital to a lower orbital, that electron ejects a photon.
Photon is light emission. And if it is completely dark environment and your thermoelectric doesn't emit light, where does energy go?
The word's very similar to.
Phonon?
So energy goes into thermal vibrations of lattice.
Alright.
Right? And what are the typical allowed frequencies for lattice vibrations? What are, do you have phonons of any possible frequency, or there are only several allowed frequencies?
And so in the quantum mechanics, I learned that energy is discrete. So
No, not in quantum. Nothing quantum. Just classical dynamics of lattices, concept of normal modes.
Do you know what an IR spectra is?
an IR spectra.
Infrared.
Infrared spectrometry. What's
I know what infrared is, but I don't remember what spectrometry is.
So if you have something like this, and this is frequency, right?
Right.
So Dimitri's asking, do you see this picture, or do you see it like total, like it can be in, like here, there are peaks, right?
Right.
Here, it can be anything. So do you think that when the lattice is vibrating, it can only take specific frequencies, or it can take any frequency at once?
It can take any frequency at once.
Yeah, sure.
What about if you have a harmonic oscillator?
Does it have many frequencies or just one?
Just one.
If you have two harmonic oscillators, either the same degenerate or just two frequencies, right?
Just two frequencies.
And your collection of atoms in your nano wire is just set of harmonic oscillators. It's like balls of springs, right?
Mm-hmm.
And they have certain frequencies at which they are allowed to oscillate. It's not any frequency, it's only certain frequencies, and they are very certain for each material,
All right.
right? And your energy from electronic degrees of freedom can dissipate into phonons only if energy offset of your electronic levels is in resonance with frequencies of these oscillators.
All right.
Okay? And there is a trend that typically for materials at lower frequencies, there are much more normal mode frequencies. Normal mode frequencies are typically in the low energy range.
All right.
So there are no oscillations with energy more than like 0.4 eV. Everything, all other most normal mode frequencies are in low energy range.
All right.
So the lower offset between electronic states the higher the probability that there will be a resonant normal mode that will accept this amount of energy. Make sense?
Mhm.
So, and the equation, your first equation, it is experimental observation, just roughly summarizing this trend. So it doesn't need to be always correct, but it is more frequently observed rather than not.
All right.
And 3 of 5 lines that you generated support this law, and 2 contradict by some reason, which is interesting.
All right.
Keep going if there's something more.
All right, and these are my calculated rates for the relaxation rate of the electron hole. And these are my decay constants for the electron relaxation rate. Yeah, this 900 temperature line is really weird, and I'm not sure why it has such a weird slope, but the other three lines look normal.
I would say opposite. The yellow line looks normal because it supports this law, and all others are abnormal.
Because the alphas would then be negative.
There is an additional mechanism if you go deeper in the band, higher in the band. Their density of states is much higher, and there are more and more parallel channels, where this black hole is designed for only a single channel.
And that ends my talk. Thank you. Any questions?
I think would like to generate right now verbal conclusions. How would you conclude it, or what is the take-home message that you want to teach us?
Okay, so basically, the summary is basically these two graphs. For my first graph, the relaxation rates of electrons. I just wanted to conclude that these three are consistent with this law right here on the board, and that these two are inconsistent. So I want to double check my results, see if I didn't make any computational errors, and then if not, I should investigate this further, trying to figure out the reasoning why these two contradict this law. And then these three results at 300, 700, and 1100, they contradict this law. Only the 900 one follows this law. So like with the last graph, barring any computational errors, I want to try and figure out why that is.
So, is there any conclusion related to the application that you're trying to understand? Because there's a lot of relaxation rates which just tell you how fast the particles relax to the band gap, but how fast is less important, I would assume, than where they go, right? Because if you have heat, it can be generated slower, right?
Mhm.
And you can still have separation of your electron and hole.
All right.
But you only concluded about the rates, not separation. Does that make sense? Yes. Because your application is to separate the electron and hole into spatially localized so that you can pop them out and make a current.
Right.
So as of right now, you're just looking at how fast they relax to the band gap. But that isn't like pointed towards your application. Does that make sense? Does the question I posed make sense?
In other words, like, for your application, what do you want? Is that fast relaxation and decay or slower decay? Which one is the favorable for these two?
Like, does it matter if it takes a picosecond or 10 picoseconds?
I basically want a longer relaxation rate, a longer electron relaxation rate. If I have a longer electron relaxation rate, that means that thermoelectric material is better.
How? Are you going to be harvesting electronically hot charge carriers, or are you going to be harvesting charge carriers at the homolumal gap?
Harvested hormone.
So isn't it more important where they end up than almost how fast they get there?
Yeah, that's something I didn't think about. I thought it was about how fast they got there.
It is important that they go there quickly.
What about the relative speed?
Yes.
That's could be expected, right?
Yes, but if the relative speed, if it doesn't localize where it needs to go, it doesn't matter how fast it does. Your system's still not working. Where, as of yet, most of the conclusions,
But even if they localize to the same spot, one gets there first, there's a chance it can leave before the other. That's all.
yes.
Hmm.
Okay.
So it is open question how to connect this little piece to overall engineering problem, and there are several directions which may or may not need to be pursued. For example, one can just assume a thought experiment, a pulsed thermoelectric, or instead of gradient of temperature, you have a very small unit which you put to the hot environment, to the cold environment,
So,
to the hot and to the cold, and then you have
No, cycle?
something like that. And then you take the voltage out of the leads.
Okay.
Then you excite when you heat it up, and then you immediately bring it to the like liquid cold environment, and then check if voltage appears.
That seems like very inefficient.
Any other questions?
Everyone is satisfied? Just curious.
It's very interesting. I mean, why you design this two-to-system? Why not just one and then the pure? Two iodine and two sodium. Is that
You're saying why I put two sodiums and two iodines in my system as opposed to like one sodium, one iodine, or
and adding the periodicity on the side? Is it inspired by any experimental result or any other reason?
I am unsure of that. I mean, I personally just chose this configuration at random. In the future, I might decide to test like other configurations, like one sodium, one iodine, or like three sodiums, three iodines, and just look at the results from those systems and then see how they compare to each other. That's another like possible research idea.
Chavez, there is a, I do not have the right word, but practical aspect of just comfort of calculations. The calculations without spin polarization and without spin orbit are a good start, which is much more inexpensive than anything else. So you do not want to deal with any spins. And if you put one dopant which has one electron more, one electron less, then it will be high chance for additional error. and if tokens come in pairs, then single configuration could be a good approximation to check what is going on. So it's intentional to avoid non-single configurations along the dynamics. In a simplified.
So would there be any logical reason to decrease the distance between the same type of dopant and so like move the top blue down and the magenta up, the bottom magenta up, so your two dopants are close, and then you have a bigger area of no dopant?
Mm-hmm. Yes. If Kevin decides to study it for like 4 years, there could be several options to check that. Concentration is one of the experimental parameters, and one can use less or put the dopants more frequently and see how it would affect the overall effect. Very good discussion. Many thanks for everyone who contributed and inspired. Thank you, Kevin, once again, and meeting is dismissed.
So anyone for next Friday? Any volunteers?
I'll take care of you.
Right. Did you want to speak to me about something?
Anyone?
Okay.
that
Thank you
wants-
much. Thank you.
Then,